Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. So in chapter number 4 we will discuss about the first law of thermodynamics, but now we will cover what we call the system involved is open system, or we call control volume system. Okay, in terms of content for chapter number 4, generally we will discuss a few principles for open system. First, we discuss about the conservation of energy for the open system, and then conservation of mass, and also the steady flow process. So these are in terms of what I call the new principle that we will learn in chapter number 4. Okay, so the rest we discuss in terms of how we want to implement this principle to different type of open system, such as I call the nozzle and diffuser, turbine and compressor, throttling valve, mixing chamber, heat exchanger, and the last one I call the system involving pipe and also duct flow. Okay, so these are the content for chapter number 4. Conservation of energy and mass for control volume, or for the open system. Okay, now about energy balance equation for the open system. So previously in chapter number 3, when we discussed about the closed system, so we already discussed about this equation, where we have energy balance equation equal to E in minus E out equal to delta E system. So the unit will be in kilojoule. Okay, so E in minus E out refer as the net energy transfer, and delta E system refer to the energy change of a system, delta E system. So if we elaborate this equation, so E in minus E out equal to Q in minus Q out plus W in minus W out plus E mass in minus E mass out equal to delta E system. Okay, so in terms of rate, so we have E in dot minus E out dot equal to Q in dot minus Q out dot plus W in dot minus W out dot plus E mass in dot minus E mass out dot equal to dE system over dt. Okay, so the second equation based on the rate of energy. So Q in minus Q out plus W in minus W out plus E mass in minus E mass out is also referred as the net energy transfer, and delta E system refer to the energy change, as I mentioned before. Okay, now previously in chapter number 3, when we discussed about the closed system, energy of a fixed mass or fixed system, or we call non-flow or closed system energy. So if you look at the schematic diagram, which is show us the piston cylinder device, when we discuss about the closed system, the system not allow any mass transfer across the boundary. However, the closed system only allow energy transfer through the boundary or cross the boundary of the system. Okay, so no mass allowed to cross the boundary for the closed system. Okay, so for this case, the term for E mass in minus E mass out will be equal to 0 for the closed system. However, for the energy of flow stream system, or we call flow system, or we call open system energy. Okay, so as shown in the schematic diagram, shows the what I call example of a compressor. So we have inlet and outlet. So for the open system, we allow energy transfer across the boundary, and also we allow mass transfer across the boundary. So mass allowed to cross the boundary of the open system. So now the term for E mass in minus E mass out in the energy balance equation will not equal to 0. Okay, so we need to consider term of E mass in minus E mass out in energy balance equation for the open system. Okay, so that the difference between what I call the energy balance equation for the closed system and also for the open system. Now we will discuss about the energy balance equation for open system. Sometimes we call control volume system or flow system. Okay, so we have this general energy balance equation: E in minus E out equal to Q in minus Q out plus W in minus W out plus E mass in minus E mass out equal to delta E system. Okay, so we have two components here. We have net energy transfer, and also we have what I call total energy change for a system. Okay, so for delta E system, previously for the closed system in chapter 3, we already discussed the longer equation, the specific equation for delta E system for the closed system, where we have we consider this schematic diagram where we have delta E system for the closed system equal to delta U plus delta KE plus delta PE. Okay, internal energy plus kinetic energy and also plus potential energy of a system, which is overall system. Okay, so how about the energy change for the open system? So actually the delta E system for the open system also have some sort like similar equation with the closed system. However, because for the open system analysis, most of the time will involve with mass flow rate or rate of something. So we will consider the equation in terms of rate of energy change. Okay, so in terms of delta E system, we will consider delta the rate of energy change for the open system. Okay, and also we consider the steady flow process when we analyze the open system. So now the term in terms of delta E system, which is referred to dE system divided by dt, will be equal to 0. So by considering the steady flow process for the open system, we already simplified the energy balance equation for the open system. Okay, so now our consideration is we want to determine what I call the equation for E mass in and also E mass out that we will use for the energy balance equation for the open system. Okay, so we need to consider E mass in and also E mass out equation. Okay, so E mass in, E mass out actually refer to mass flow energy transfer. Before we go further to discuss about the energy balance equation for the open system, we need to know what I call different terms that we use for mass. Okay, so we have mass and volume flow rate. So for mass, the unit will be kilojoule. So the formula for mass, M equal to rho, stand for density, multiplied by volume. Okay, also equal to volume divided by specific volume. So this is the formula for mass. Okay, in terms of mass flow rate, the unit will be kilogram per second. And we have a few parameters that we need to know based on this schematic diagram, where in the schematic diagram we have a cross section of a pipe. Okay, so we have fluid flow and density of the fluid, and the curve, the red color line curve represent the velocity distribution of the fluid inside the pipe. And normally during our calculation for the open system, the velocity for the fluid normally refer to the average velocity, which is represented by the distribution of velocity represented by the blue color arrow that represent the distribution of average velocity, V average. And we have AC stand for cross-section area of the pipe. Okay, so the value of AC or the formula for AC depend on the shape of the cross-section area. And also we have M dot, which is referred to the mass flow rate symbol. Mass flow rate equation, M dot equal to rho density of the fluid multiplied by average velocity, V average, multiplied by cross-section area, AC. So this equation also equal to density multiplied by volume flow rate, V dot, capital letter, and also equal to volume flow rate, V dot, divided by specific volume. So this is the equation for mass flow rate. And for the volume flow rate equation, in terms of unit will be meter cubic per second. Okay, so V dot, the symbol for volume flow rate, equal to V average multiplied by AC, cross section area, also equal to V bar multiplied by AC. So now we will use in terms of symbol for average velocity, we will use V bar in order to differentiate between the V symbol for specific volume and also the symbol for the average velocity. Okay, further, before we consider or we discuss about the conservation of energy for the upper system, we will need to know a new principle that we call conservation of mass principle. So later on we discuss about this principle, which is referred as the conservation of mass principle. Example 4.1. So this example actually involves with what I call the equation for the mass, volume flow rate, mass flow rate, and so on. Okay, so example 4.1, a garden hose attached with a nozzle is used to fill a 40-liter bucket. The inner diameter of the hose is 2 cm and it reduced to 0.8 cm at the nozzle exit. If it takes 50 seconds to fill the bucket with water, determine A, the volume and mass flow rates of water through the hose, and B, the average velocity of water at the nozzle exit. So now try to draw a simple schematic diagram to describe the problem involved and put whatever data given. So as shown in the schematic diagram, so we already have the what I call the diameter of the hose and also the diameter of the nozzle at the exit, and the amount of what I call water required to fill in the bucket is 40 liter. And also we have the time that required to fill in what I call the bucket up to 40 liter of water. Okay, so now we need to determine the volume flow rate V dot, mass flow rate M dot, and also the average velocity of the water from the hose V bar. So the average velocity at the exit of the nozzle. Okay, so now for the volume flow rate V dot equal to V, volume, divided by delta T, the time that required by the process. So V dot equal to 40 liter divided by 50 second. So we'll get equal to 0.8 liter per second. So that's the value for volume flow rate. For water, 1 gram of water more or less equal to 1 milliliter. So for mass flow rate, if you compare to volume flow rate, the value of mass flow rate actually equal to the volume flow rate. So now we have the volume flow rate equal to 0.8 liter per second. So we just equalize the value because 1 gram of water equal to 1 milliliter of water. So M dot will be equal to 0.8 kilogram per second, where we just replace 40 liter with 40 kilogram. So 40 kilogram divided by 50 second will be equal to 0.8 kilogram per second. Question B, we want to determine the average velocity of the water. So at the nozzle exit, so we know that the what we call the average velocity V bar at the exit of the nozzle equal to volume flow rate divided by cross section area of the nozzle exit, AE. So calculate what I call the area, cross section area for the AE, where we will use the formula for the what I call the area of a circle. So AE equal to pi multiplied by radius RE power of 2, which is equal to pi multiplied by 0.4 times 10 power of negative 2 meter square. So the value of AE equal to 0.5027 times 10 power of negative 4 meter square. So that's the value for the cross section area at the nozzle exit. 1 liter equal to 1 times 10 power of negative 3 meter cubic. Okay, so substitute all the value. First we change what I call the value, the value of volume flow rate meter cubic per second. And then substitute all the value that we have for volume flow rate and also the cross-section area at the nozzle exit into the equation for the average velocity. So we will get the value of average velocity at the nozzle exit equal to 15.9 meter per second. Okay, so that's example involve question example of the question involved with mass flow rate, volume flow rate, average velocity, and so on. Okay, now we will discuss about the conservation of mass principle. So in terms of concept or definition for the conservation or explanation for the conservation of mass principle, the principle mentioned that the net mass transfer to or from a control volume CV during a time interval delta t is equal to the net change in the total mass within the control volume CV during the time interval delta t. Okay, so if you want to get clear understanding about this principle, let us discuss about the specific case or specific system. Okay, as shown in the schematic diagram, where we have initial state at time number 1. So we have a tank with one inlet and also one outlet, and the dash red color line represent the control volume boundary, and the substance or the system inside the boundary we consider as control volume CV. Okay, we have one mass in at the inlet and one mass out at the outlet. Okay, so the mass of the control volume we consider as MCV for the initial state. Okay, after a certain period of time, delta t, so we have final state at time number 2. Still we have continuous mass into the tank at the inlet and mass out from the tank at the outlet. And we have new value of MCV for the final state. So if you compare both states, we will have mass change, and this mass change refer to the delta MCV, which is also represent the net change in the total mass. Okay, so the M in and also M out actually refer to the mass transfer of the system. Okay, based on the conclusion or the definition of the conservation of mass principle as I mentioned before, so this system actually refer to the single stream system, and the equation involved with mass will be refer to the conservation of mass principle, where in terms of mass form, so we'll have M in, mass in minus mass out equal to delta MCV in kilogram in terms of unit. So M in minus M out represent the net mass transfer, and delta MCV represent the net change in the total mass for the system. And delta MCV also equal to MCV for the final state minus MCV for the initial state. So this equation also we can present the equation based on the mass rate form, where M in dot minus M out dot equal to dMCV over dt in kilogram per second, where dMCV divided by dt equal to MCV dot for the final state minus MCV dot for the initial state. Okay, so we have another example. So now this example will show you what we call the example for multiple or a multi-stream system, where we have multi-stream system refer to the what we call the number of inlet more than one, and also the number of outlet more than one. So we consider that system as the multi-stream system. So let's say we have initial state at time number 1, and this is schematic diagram for the system, where we have now specifically we have 2 inlet and 1 outlet for the system. Okay, so we have mass in at the inlet number 1, and also mass in at the inlet number 2, and we have only one mass out, and the dashed line red dashed line represent the control volume boundary, and whatever substance inside the boundary we consider as the control volume. And the mass for the control volume we refer as a mass of the control volume at the initial state. Okay, after certain period of time, so we have the increase of control volume mass, okay, where we have continuous mass in at the inlet number 2, and also we have continuous mass out at the outlet. So we'll have new value of MCV at the final state, and also we'll have mass change, which is referred to delta MCV. Okay, so for the multi-stream in terms of equation in mass form, so we have sigma represent the total or summation of something. So sigma m in means the total of m in, mass in minus the total of m out, equal to delta MCV in kilogram, and delta MCV equal to MCV final minus MCV initial. In the mass rate form, the equation will be summation or total m in dot minus the summation or total m out dot equal to dmcv over dt, and dmcv over dt also equal to mcv dot final minus mcv dot initial. And this equation actually we can call, or we can consider as the mass balance equation, the general equation for the mass balance equation. Okay, so if we implement this equation to the what I call the second schematic diagram, so what we will have, the final equation will be m in dot 1 plus m in dot 2 minus m out dot equal to dmcv over dt. So that's the final equation for the second schematic diagram. Okay, so that the explanation for the conservation of mass principle.